Log on, tune in, find out. Another good idea from Cambridge.
So first, do you hear me? That's the microphone. Oui. Okay. Okay, so first I would like to thank the organizer for the invitation to this workshop and also to the kinetic semester. So I will not speak about the Schrödinger equation, but the quantum Boltzmann equation. So actually my main work is devoted to the approximation and study of the Boltzmann equation, and here I will try to enter in the scope of the workshop and so speak about quantum Boltzmann equation, even if this work is much more general. In fact, I started to work on this program almost 10 years ago, when I started to work with Giovanni Russo and Lorenzo Pareschi on the approximation of Boltzmann equation by spectral method, and then we continue to work and to have a better understanding of this method with Clément Mouot. And more recently, we started a project with Chijin on the approximation of the Boltzmann equation in the multi-scale when we have a different scaling. So first, the aim of this work will be in two parts. First, I want to develop some accurate numerical method for the approximation of the Boltzmann equation that is written here. So of course everybody knows that here f, the distribution function, depends on time, position x, and velocity v. The first part is just a transport equation. It tells you that some particles are moving with the velocity v, and then they collide, and the collision operator in the quantum kinetic, let us say, framework is described by this operator here. So it looks like a quantic operator, even in fact it is only cubic, but we can split this operator in two parts, q plus, which is a gain term, and the loss term, q minus. So of course, there is a microscopic picture for the collision, to describe collisions between two particles. So for instance, you consider a particle v and a particle v star. They collide with where you assume that there are conservation of momentum and energy, and after that, after this colliding picture, you find two new velocities, v prime and v prime star. And so we denote here by f prime correspond to f of v prime, etc. Here in this talk, I will assume that the cross-section B only depends on relative velocity v minus v star and the vector omega of the unit sphere, and so and even in fact the cross-section B will be assumed to be equal to this quantity here. Okay. So in this talk, I will not, in the first part, I will not speak about the conservation and modeling part. I will just concentrate on the collision operator and see it as an integral operator. And my aim will be how to approximate an integral operator using a spectral method. So to do that, I will first reformulate the Boltzmann equation in a framework to apply some Fourier-Galerkin method. Then I will address different problems. The first one is the computational cost. Of course, here we approximate a kinetic equation with a deterministic method, so you really have to take care about the computational cost if you want to compete with the different method as Monte Carlo method, for instance. Then I will address the problem of stability of this kind of method. This is a joint work with Clément Mouot. Actually, it does not really apply to the quantum Boltzmann equation, but I would like to tell some words about that. And then I will be interested by the accuracy of the method, and I will show you what is the spectral accuracy on this. And then my second part will be devoted to the stability of the numerical method. So this is a joint work with Xi Jin and Jingwei Hu, who are both in Madison. So in fact, we studied this problem because the quantum Boltzmann equation is a very nonlinear problem, and we were looking for nonlinear equations. So, and you will see how we have applied a very simple method which allows us to get some uniformly stable, to build some uniformly stable schemes. And finally, I will present different numerical simulation to illustrate the accuracy of such a method when we consider different regimes, hydrodynamic and kinetic regimes. So let us start with the Boltzmann equation. So I will first forget about the transport term and just consider the homogeneous Boltzmann equation, so where I only consider time and velocity v. And I will focus here in this talk in the approximation of the Boltzmann operator here. So here I will consider that the quantum Boltzmann equation reads like this. So it is an integral operator over a domain that I will denote by capital C. And here I will assume that the cross section capital B only depends on the integral variable. The variable of integration, sorry. And then I have to define what are v prime star, and v star. And to do that, I will assume that v prime star, and v star can be written as the sum of v, which is the point where I compute my collisional operator, plus a function of the variable of integration y here. So I assume that theta prime star, and theta star are given functions. In fact, they only describe the collisional mechanism of my operator. But here, so I just if I resume, I just consider a collisional operator, an integral operator over a domain capital C, and I assume here I set that v prime star, and v star are given in this way. It means that there is some invariance by translation. Then so first you can observe that the Boltzmann equation that I have written before is not on this form. So I have to perform some change of variable. And for instance, if I just set in the quantum Boltzmann operator u equal to v minus v star, the relative velocity, then the q of f can be indeed written in the previous form. So here the variable of integration is u omega, where u is the relative velocity, and the function. So the domain of integration is rd times the unit sphere. And finally, v prime star, and v star are given by this. So indeed, it is written as the sum of v plus a function of u and w, and we can check this for v prime star and v star. So indeed, it enters in the framework that I described before. In fact, there are different formulations for the Boltzmann equation, and if I use the Kalman representation now, where I change a little bit my domain of integration, I consider capital C as Rd times Rd. It's just to take into account some symmetries in my operator. Now the variable of integration are u and z, and the cross section is indeed just a function of u and z, and I have a Dirac in order to assume some orthogonality between u and z. And v prime and v prime star and v star are still given by a sum of function v plus a function theta. Okay. So now, I have to. We can rewrite the quantum Boltzmann equation as the sum of the classical Boltzmann operator plus 4 operators Q1, Q2, Q3, and Q4, which are given by this formula. And here, I will not describe the numerical method for all of them, but I just want to focus for the most non-local operator, I mean Q1, which is written like an integral over f prime star, and f star. So here, you see that this operator is really non-local, since there is no dependence of f of v, whereas for Q2, Q3, and Q4, there is everywhere f of v. So it is, there are some local aspects here. So here I will concentrate on how to approximate this operator Q1. So as I told you, Q1 of f is really a fully non-local operator. And using a change of variable, as I told you before, I can rewrite it as an operator like this. Now, to describe a numerical scheme, there are mainly 3 steps. The first one is to reduce the domain of integration capital C in a bounded set that I will denote by CR, where R represents a truncation of this domain of integration. Also, I have to find a bounded set for the velocity domain that I denote by DL, and of course, all the variables L and R are linked together. I don't want to enter to give you all the details to compute them, but it is possible. For instance, this is done in the work of Lorenzo Pareschi and Giovanni Russo. If you assume that the distribution function is compactly supported, then you can compute the truncation of the computational domain C, and also the computational domain for the velocity v. Then you just approximate the distribution function f by a truncated Fourier series that you denote by f capital N, which is given by this quantity here. This is the truncated Fourier series, and fk hat are given by the Fourier coefficient. And then you substitute this new distribution function fn in the collisional operator Q1, and you compute. And what you get, in fact, using here it is really important to consider that we use a Fourier series because what you want to do is just to decouple the variables, and so when you compute the distribution function f of v star, for instance, fn of v star, it will be given by a sum of a Fourier coefficient fk hat times the trigonometric polynomial exponential of a. Okay, let us take p equal L of k of v star. And now I remind you that v star is given by v plus a function theta star of y, and using the property of the exponential function, then you can decouple the variable v and y, and then you get now for your truncated collisional operator Q1 a formula like this, where you decouple v and the variable of integration y. Then these since the collisional operator Q1 is a cubic, you have a sum over L, M, and N of which are multi-integers actually, and you compute it is the sum of this coefficient beta of L, M, and N times the Fourier coefficient of f, and times a trigonometric polynomial which is given here. Now you can use the orthogonality property of trigonometric polynomials. You multiply this formula by exponential of AP over L kV, and you integrate, and then you get a system of ODEs for the Fourier coefficient Fk hat. Then you see that solving the Boltzmann or approximating the Boltzmann equation by a Fourier-Galerkin method, only you just have to solve this system of ODEs here. And what is really important here is that it doesn't matter the conservation properties or the structure of your operator, what is the physical properties of the operator. What is really important here is the algebraic structure of your collisional operator, and the main property is the invariance by translation, which is given here. And then finally, approximating the Boltzmann equation by a Fourier-Galerkin method can be described by this equation here, where you approximate your initial data by a truncated Fourier series, then you compute the collisional operator. You apply the collisional operator to this truncated Fourier series, and then, since it is a cubic operator, you project here capital Pn is a projection operator on the trigonometric on the set of trigonometric polynomial of degree capital N. And finally, you can write the numerical method in a continuous level, solving this equation here. So there are mainly 3 steps: approximation of the initial data, truncation of the collisional operator, and projection. So actually the approximation of the Boltzmann equation by spectral method is a long story. They started in the 90s by Pertam and Paresky, and also Bobilev and Razanov. They modify a little bit this numerical method in order to get some conservation properties as there are in the continuous level. Then Giovanni Russo and Lorenzo Paresky give explicit expression for the coefficient beta Lm. I didn't speak about that, but you see that there is something strange here, that you have to compute this kernel beta of Lmn, which is a huge kernel, and it involves an integral over a 5-dimensional domain if you consider that you are in R3. But actually, you can reduce this domain of integration by a simple integral of dimension 1, and even for physical cases, as Maxwellian molecules or hard sphere, you have explicit expression of this coefficient beta L and N. Forget. So in fact, it doesn't matter. The computation of this coefficient for interesting cases is really an easy thing. Now, so these works concern the approximation of the classical Boltzmann equation, which is a bilinear operator, and for which the computational cost is in n square. And more recently, together first by Bobilev and Razanov, they propose a fast algorithm for which the computational cost is in n log n, where n represents the number of degree of freedom. And also, more recently, with Clément Mouot and Lorenzo Paresky, we also, using the Karleman representation of the Boltzmann equation, we modified the spectral method in order to get fast algorithm, still in n log n, and keeping the spectral accuracy I will discuss later. Concerning the quantum Boltzmann equation, there are actually few works. I quote, for instance, a paper by Markovich and Paresky, where they get fast algorithm also to approximate this operator, but the idea is just to approximate the Boltzmann equation by some quantum Landau-Fokker-Planck equation, which can be written as a a convolution operator. So in that way, it's easy to get fast algorithm. Okay, now let me focus on the computational cost. So first, I have to deal with this coefficient beta of LMN, but now I didn't prescribe before the function theta prime, theta star, and theta prime star. But now, using the function that are given by the Kalman representation, describing the collision mechanism of the Boltzmann operator, we can rewrite this coefficient only as a function of L plus n and m plus n. And also, now, in order to get fast algorithm, the idea is to decouple the variable, this kernel here. The idea is just that we would like to write this kernel here as the sum of a product of a function of L times a function of n. The idea behind is just to write the collisional integral operator as a discrete convolution. So using these, we just apply a quadrature formula here to write the kernel beta LM in that way, and then we can we compute, for instance, the collision operator Q1, and we get this formula here. So it is not very nice, but you see that now if you fix n and p is the number of, it describes an angle discretization, so this is fixed. And now if you fix also n, you look for this formula here, and you can see that this is a discrete convolution. And using this, you can use Fourier transform, since you know that you can compute discrete convolution using with an n log n cost, and then you get a formula which is still a convolution between L plus m and Fn. Here. So finally, you get a computational cost for this quantum Boltzmann equation operator, for the operator Q1, like an n squared times log n times m, which is an angle discretization. And the computational cost is given by the computing the operator Q1. Yeah. Okay. So now I would like to discuss some stability properties of this kind of approximation. So here, what we can prove is that this numerical method preserves its mass. This is easy to check, but we lose other conservation. We know that the Boltzmann equation conserves momentum and energy. There is also an IH theorem saying that there is an entropy production. Moreover, the distribution, if you start with an initial data which is non-negative, the distribution function remains non-negative for all time. Actually, we lose all these properties for the quantum Boltzmann equation and for the approximation of the approximation of the Boltzmann equation using the spectral method. So in 2000, Lorenzo Pereschi and Giovanni Russo proposed to introduce some filters in order to preserve positivity. The preservation of positivity is really the point here, even if you don't really mind about conservations of momentum and energy, because you still have some estimate on the loss of conservation. You can prove that if the number of points is large enough, because you have the method is accurate enough, actually it's not a problem. But positivity it means that you can generate some oscillations, and so it can be dangerous. So they propose to add some filters. But now, if you modify the numerical method in that way, the method becomes first order. It means that you started with a numerical method which is very, very accurate, and finally you modify it and you get not really accurate result. So this is not really the way we want to take to analyze the stability. But we have a consistency theorem for the spectral method. Actually, since all the computations are almost exact, there are only three. I told you there are only 3 steps in the approximation: approximation of the initial data by a truncated Fourier series, a truncation of the Boltzmann equation, and projection. So, actually, using, for instance, a classical interpolation theorem of trigonometric polynomial, you can prove that if you estimate the difference between the truncated Boltzmann operator and the projected Boltzmann operator of a distribution function Fn, then you have this kind of estimate, if f is only L2. But now, if the distribution function is smooth enough, you get this estimate where you see that the rate of convergence here only depends on the smoothness of the distribution function. So when you change R, assuming more regularity on the distribution function, then you improve your regularity. So this is typically spectral accuracy, where the order of accuracy is not fixed by the numerical method, but it only depends on the smoothness of the function that you approximate. So recently, with the Clément-Mouot, we started from this theorem, which tells you that the method that we apply to approximate the collisional integral operator is a super consistent method. So the idea is to study the stability of this numerical method, just saying that you consider that your numerical method, let us denote it by Qn of Fn, and R is for the truncation, is just the sum of the truncated Boltzmann operator, so it's Qr of Fn, so this is the true Boltzmann operator, plus this one, Qn R of Fn, so here it's F, sorry, minus Q R of F. And since you have an estimate on this difference here, you can use all the good properties of your Boltzmann operator that you perturb and analyze the stability of the perturbation of this operator here, of the initial one. Okay? And since you can estimate the difference using the consistency approximation, you just have to study the stability properties of this operator here by a perturbation which does not conserve positivity. And so we get all the estimate proving that in fact the solution, even if on a short time you have some oscillations, after a while the solution becomes still positive. Unfortunately, it's very difficult to apply such a method, such a stability method for the quantum Boltzmann equation, because we don't have the bilinear structure that we strongly use in the previous study. So this is still an open problem to study the stability of spectral method for the quantum Boltzmann equation. Okay, at least we can perform some numerical simulations just to see if the method is really accurate. And so here you have an illustration of the spectral accuracy. So we consider an exact solution of this is for the classical case, for the Boltzmann equation. And here the line represents an approximation for, let us say, n equal 8. Then you multiply the number of points by 2, 16, and then 32, and so the dots represent different kind of approximation with different angle, but we don't care here. I just want to show you what is spectral accuracy. It means that here the order of convergence, it is something like equal to 4, but when you increase the number of points, we also increase the order of accuracy, and here the order of accuracy become 8. It is, of course, because we started from an initial condition which is C infinity. So we really, in that case, we have a very good accuracy of the method. We can also apply this kind of approximation for the quantum Boltzmann equation for the two cases, for both gaze and Fermi gaze. And in that case, you see that we have a different order of convergence. Okay, so something like you can reach 20 and okay. So now I would like to discuss the second part of my talk, which is the approximation of the Boltzmann equation, but when you have an additional parameter, 1 over epsilon, in front of the collisional operator. So now I will assume that I know how to approximate Q of f, and I will focus on the stability, stability properties of this problem here. So now you have to go to the physics and remind you that the collision operator Q conserves its mass, momentum, and energy. It means that some momentums, the first momentums of the collision operator, are equal to 0. Then you define the density rho by integrating the distribution function with respect to v. You define the momentum rho u by computing the integral of f of v, and you define here the internal energy that you define like this. Okay. You also define the pressure tensor and the head flux in that way, and then if you multiply your Boltzmann equation by 1 v and v square, you get this system of PDEs, and of course it's not a closed system, and to close it you have to use the entropy principle, or the prediction of entropy, which tells you that when the entropy is 0, it means that the distribution function is this quantum Maxwellian, which is given by this quantity here. So here there is a difficulty. So of course there is a sign minus and plus depending if you consider boson or fermion gas. Here there is a parameter z and t that I didn't define, but actually they depend on the density rho and the internal energy E in a non-linear way. So it means that if you know rho, if you know this quantity, the invariant, with respect of your collisional operator, if you know rho, u, and E, you can compute the parameter z, u, and t, but z and t are given in non-linear way and they are not explicit. So it's very difficult to compute these quantum Maxwellian here in practice. So now what is the idea to get stable scheme for the approximation of the quantum Boltzmann equation? So still the transport part is not really a problem, so I will focus on the numerical resolution of this stiff problem. It is stiff because the parameter epsilon goes to 0. So the idea is just to split the collisional operator in two parts, where you introduce a new operator, P of f, that will be defined later, and you want this operator is such that Q minus P is a non-dissipative operator, whereas P of f is a dissipative part. So now you have to define what is P of f, and in order to define it, you want to conserve the structure of your operator. So, for instance, you would like that P of f has the same steady state of Q, and also the same invariance. And also you want to consider the differential structure of your operator. Even here it is an integral operator, so we don't really mind. And of course, since the idea is to apply an implicit part, an implicit scheme on the operator P of f, so you want this operator to be easy to invert, to treat by an implicit scheme. So now, to find what is P of f, the first idea, of course, is to perform a Taylor expansion of the operator Q of f to linearize it around the equilibrium M of Q. And so finally, you can choose your operator P of f given by this linear operator here. Unfortunately, this approximation is still a non-local operator, and it is an operator which is very complicated to compute. So already the structure of the full operator Q of f is complicated, and so you didn't really improve things by introducing this linearized operator. Moreover, there is another problem which is typical for the quantum Boltzmann equation, is that it's very difficult to compute explicitly the quantum operator M of Q. So the idea now to treat this, let us focus on this problem here, where you split the non-dissipative your operator in a non-dissipative part and dissipative part. In order to understand how to design a scheme, I would like to make a first digression, very simple digression concerning a problem of ODEs. I think everybody knows that, but if you consider a linear ODE and with a lambda which is given, you know that if you consider that you have a dissipative problem, I mean the real part of lambda is strictly positive, in that case you want to use implicit scheme in order to get uniform stable schemes. And so in that case, if you apply an implicit Euler, the numerical solution is given by this. And your solution is stable, and it has the same behavior as the exact solution when n or when epsilon goes to 0. It converges to 0. Actually. Now, if you consider that your real part, this is not really known, but now you consider that the problem is not dissipative, in that case, if you apply an implicit scheme, the scheme is not uniformly stable. If you have a non-dissipative problem, you have to apply an explicit scheme. And in that case, the solution of this, the numerical approximation of this system of ODEs using a Euler explicit scheme is given by this. And in that case, if the real part of lambda is negative, the numerical solution is uniformly stable. You don't have to impose any condition on delta t on delta t in order that the numerical solution is stable. So it's exactly what we want to apply to our problem now. So I mean that this term will be treated either implicitly, for instance, implicitly, and the non-dissipative part will be treated explicitly. So actually there are two approaches. The first one, if you just take P of f equal to a BGK operator where lambda will be computed later, and you have to think that lambda is large enough in order that the operator Q of Q minus P is non-dissipative. In that case, using the Duhamel formula, you can write your solution of the initial problem in that way, and then to apply a numerical scheme, now you have to discretize this integral, and this you can do using an explicit scheme, since this part here is non-dissipative. And the scheme, it gives you such a scheme, and you see that if when epsilon goes to 0, this term cancels here, and then the solution converges to the quantum Maxwellian. Okay. So in that case, you really get an AP scheme, let's say, where when the epsilon goes to 0, the numerical solution converges to the quantum Maxwellian. Now there is another strategy which is more simple. We just apply an IMEX scheme. By IMEX, I mean implicit, explicit scheme. So we just treat the explicit part here, the non-dissipative part by an explicit scheme, and then the implicit part, and the dissipative part by an implicit scheme. And this is the strategy we want to use. Just, maybe I will not write. Just a remark that for the first scheme here, which is given here, we can analyze this scheme and prove uniform stability, and also that the numerical solution converges to the steady state exponentially fast. Not for the quantum Boltzmann equation, but for a baby problem, which is the relaxation problem with the nonlinear relaxation operator. Okay. Now, for the second scheme that I want to apply here, we have. So, is it a good idea? Yeah, sorry, I will just. Yeah, okay, we'll speak about this. So we have some properties. If we have enough assumption on the approximation, some estimates that are very difficult to prove, we prove that the scheme is consistent, and we have a kind of stability properties, which means that when when the times goes to infinity, I mean n goes to infinity, the numerical solution converges to the steady state with an approximation which is of order of epsilon, and here this coefficient is between 0 and 1, so this term goes to 0 when n goes to infinity. So it means that the IMEX strategy is not AP in the rigorous sense, where in one iteration, if epsilon goes to 0, we reach the steady state. Here we need some time iterations in order to converge to the steady state. Actually, there is another difficulty for the approximation of the quantum Boltzmann equation. As I told you before, this quantum Maxwellian is very difficult to compute, since the relation between z and t is fully nonlinear with respect to rho and e that represent some invariance of your Boltzmann operator. And the relation are given by these, where q here is a given function. I don't want to give the details on this. So what we propose with Shijin and Jingwei Hu is to replace this quantum Maxwellian by a simplified Maxwellian, which is the classical one, where we compute in this classical Maxwellian, the temperature is given by the internal energy is given by dt over 2. So finally, we do not use this quantum Maxwellian, but this one here, which can be explicitly computed from the invariant of the quantum Boltzmann equation, since they only depend on rho, e, and u. So in fact, there are some links between MC and MQ. C is for classical and Q is for quantum. And so it means that there are some consistency property between the two. So now, to conclude my talk, I would like to show you some numerical tests on a very simple problem. This is the 1D shock tube for the two cases where we consider Fermi-Dirac distribution and also Bose-Einstein distribution. Here I introduce a new parameter, theta 0. In fact, theta 0 measures how far we are from the classical Boltzmann operator. When theta 0 goes to 0, we recover the classical Boltzmann operator, whereas for large theta 0, we take into account on quantum effects, more and more quantum effects. So I consider this very classical shock tube problem with these initial data, and I compute the macroscopic quantities first for small values of epsilon, where we are in the hydrodynamic regime, and for a small value of theta 0, which means that we are close to the classical regime here. So here we plot at a given time the density rho, the mean velocity u. Here it is the temperature T, and here this is the fugacity Z. So we compare the solution given by the approximating the kinetic equation and the numerical solution approximating the Euler limit which is the asymptotic limit of the quantum Boltzmann equation. And you find a very good agreement between the two in this regime, even if the scheme we don't really apply to the quantum. We didn't use the quantum Maxwellian here. So this is for both gas, and now we take into account more quantum effects. We take theta 0 large enough, and in that case we still find a good agreement between the different approximations, even if on the fugacity there are some differences here. Finally, we also applied the scheme for Fermi gas, still with small values of epsilon, and in that case we still observe a difference for large theta on the fugacity, whereas for the rho, u, and t, the approximation is really correct. Now, I will just show you this last numerical test. It's for small values of epsilon. In that case, the hydrodynamic regime is not valid, but we still observe some good agreement. But here, it's very difficult to say what is the best approximation. But we observe some oscillations here on the approximation of the hydrodynamic regime, whereas the solution is very smooth for the solution corresponding to the kinetic equation. So we can really believe in it. And I think I will close my talk now. Thank you for your attention.
Other questions, comments?
Do you have some simulation in the case of Bose gas? For example, with respect to this Bose-Einstein condensation?
So here we have applied, I didn't tell it, but we have applied for the numerical method for 2D in velocity, and in that case we don't have Bose-Einstein condensation. We really have to go to 3D problem. So still the computational cost is really huge for this problem. So it's very difficult to apply such a scheme for the real 3D in velocity.
And for example, if you look for the isotropic version, can you?
Maybe it will be better, but in that case, I'm not sure that you can really apply for the non-homogeneous case, because when you apply the transport part, you break the isotropic structure. So, okay, maybe you can make some assumption and saying that okay, the solution will not be too far, but it's difficult to.
Other questions? No,
Thank you.
Again.